Hello students, welcome to class 12 physics class. Today we discuss magnetic effect from the chapter magnetic effect of electric current, few derivations. As earlier I will upload that video related to that derivation, but the statements are not there. As per some students request, I will again upload this that derivation, and with some numericals also be there. Okay, in that video on derivations are there and the steps are there with a slide. Okay, that's why the statements is not there, but in your when you write in an exam you have to write the statements. That's why again I will make this video in short with the statement. I hope you understand the previous video of this. Just again I will revise that one, and then I will discuss the four numericals related to these derivations. So as we discussed in the earlier video, that the magnetic effect of electric current is one of the effect when the electric current is passes through a conducting wire. We know that there are three types of effect: heating effect, magnetic effect and chemical effect. And magnet is a substance which attracts a small piece of iron, cobalt, nickel, etc. That is the magnetic substances, and the space or region around the magnet within which its influence can be experienced is called magnetic field. And from Oersted experiment we conclude that whenever a current is flowing through a conducting wire, a magnetic field also created around this wire, and that's why the magnetic needle will be deflected. Now this video started with the Vasavat Law. This Vasavat Law is also associated with this electric field and the magnetic field also. So Biot and Savart, these two are the two different scientists. They together discovered this law. That's why this law is named as Vasavat Law. What is that law? Now that XY is a conducting wire through which I amount of current is flows. Okay, and here in this chapter, whenever we discuss the conducting wire, we also use a small part of that wire that is called current element. So here DL is a current element. We consider this whole wire is consist with small dl, and if its length is dl, then this L is the summation of this small current element dl. So we consider any small current element of this wire, that is dl, and from this current element at a certain distance, that is r, at a point P we determine the magnetic field, because from Oersted law we get that if the current is there, that means magnetic, we get also the magnetic field. So we consider a point of a certain distance, and at this point P, at this point we determine or we find out the expression or the value of magnetic field. Okay, so we can say that this R, because with a vector sign I will written over here, so R is a position vector of B with respect to this current element, and the angle between current element and this position vector will be theta. Now how we can determine the direction of dB? That is, in that video we discussed two laws, right hand thumb rule and another one is a right hand corkscrew rule. So this one is a thumb represent the current direction, so other in which direction they will move the other four fingers, that will be the direction of magnetic field. So here you see that it's current flowing through X to Y, so we put it over there like this way, and if we move our four fingers like this way, that means it is into the paper, inward direction normally, but inward direction into the plane of the paper. So when the direction is into the plane of the paper, it will be denoted by cross. So at point P, due to this dl, the whatever the magnetic field is created, that direction is normally into the paper, normally or perpendicularly, anything you can write. They will be normally or perpendicularly into the plane of the paper. Okay, so what is this Vasavat law? Vasavat law states that the magnetic field dB at point P is directly proportional to the magnitude of the current If we increase the current, the strength of the magnetic field also increases. This dB is also proportional to the current element, that is dl. dB is inversely proportional to the square of the distance between the point and the current element, and dB is proportional to the sine theta. This theta is a very small angle, that's why we consider as a sine theta. So if we combine this four law, we get dB proportional to I dl sine theta by r square. Now in place of proportional sign, if we use the equal sign, so we have to multiply it by a constant term, that is k ideal sine theta by r square. Here k is the proportionality constant. And in SI unit and for free space, if we consider in between the DL and P point, here the space is free space or the air medium or the vacuum medium. And if we determine in a SI unit, so the value of K is mu 0 by 4 pi. Mu 0 is the permittivity of the free space. So in place of K, if we put it over there, dV equals to mu 0 by 4 pi ideal sine theta by r square. And the value of mu 0 by 4 pi is 10 to the power minus 7 Tesla meter per ampere, or Weber meter inverse ampere inverse. Okay. So now this equation, if we write in a vector form, so which two terms are the vector quantity, that dl and r. So sine theta means when we write down the sine theta, when the cross product is there. So we can write this expression like this way: dB mu 0 by 4 pi I dl cross r hat by r square. Because whenever we use a vector form, one unit vector also be there, which gives us the direction of that vector. Okay, so and unit vector equals to that vector by its magnitude. So in place of r hat, if we put it over there, we get mu 0 by 4 pi I dl cos r hat by r cube, because r square is there, divided by r cube. Now dl cross r means I dl r sine theta by r square. So one r cancel over there, so we get this scalar form. I hope you understand this one. Cross product means sine theta. And the direction of dV, from this equation what we can write, the direction of dV, which one is a vector quantity, only this part, dl cross r. So this depends upon this one. So dl to r, the direction of dV is the direction of the vector dl cross r. So if cross means into the plane of the paper perpendicularly, and if dotted sign over there, that means if you just change the direction of the current, if you change the direction of the current, then the fingers move outward direction. That means at point P, the magnetic field lines in an outward direction emerges from the plane of paper perpendicularly. So in whenever the direction of current is this side, opposite to this side, that means y to x. So at point P, we use this sign, dot sign. So dot means outward from the plane of the paper perpendicularly. This is the Vasavat law. I hope you understand this one. I will not take so much time for this derivation, because already I will upload one video, but because there is no statement is there, that's why again I will upload this one with the statement. Now there are some special cases also be there. If theta equals to 0, that means if the angle between DL and R, this will be 0. So sine theta will be 0, we get dB equals to 0. That means the point P lies on the wire, not at a certain distance. The magnetic field at 0 at the points on the axis of the current element. The point P also lies on that wire. Now if theta equals to 90 degrees, that means this distance is perpendicular. Okay, so then sine theta equals to 1, so we get dB is maximum. dB is maximum. The magnetic field due to the current element is maximum in a plane passing through the element and perpendicular to its axis. If that distance will be perpendicular, then we get the maximum magnetic field. I hope you understand this one. Another one application of this Vasavat law, you can say that the magnetic field due to a straight wire carrying current. Here we consider XY is a straight current carrying conductor through which I amount of current is flows. We calculate the magnetic field at a point P at a perpendicular distance of A from the wire at O. So from P to O, this is a perpendicular distance from the wire, that is 90 degree. So this distance is A. Now as usual, we consider a small current element dl through which the distance of P, that is R. This is not a perpendicular, so it makes one angle theta. So this is I will write this point as a Q. This small, very small point is considered as a point, but here if I will write as a point, you cannot understand. That's why I will write as a big size. But this current element is a very small. So this point is named as a Q. So here you see that one angle is 90 degree. So this POQ is a right angle triangle. So here theta plus phi, that is equals to 90 degree, because one angle already 90 degree. If this one is 90 degree, this one also be a 90 degree. So other two angles, sum of the other two angle also be 90 degree, because the total angle is 180 degree. So theta plus phi equals to 180 degree. So 90 degree. So theta equals to what we can write? 90 degree minus phi. So sin theta equals to sin 90 degree minus phi, that will be cos phi. Okay. So here I will also apply the Vasavat law. Here there's some language I will write, that PO, that is a perpendicular distance A, or again we consider the DL. From DL to O, this distance is L. Okay, and it makes one angle theta with DL and R. So according to the Vasavat law, what we can write? dB equals to mu 0 by 4 pi I dl sin theta by R square. As we already discussed, the sin theta equals to sin 90 degree minus phi, that will be cos phi. Okay, now we find out sin theta means what? Sin theta means from this triangle, sin theta means what? Sin theta means perpendicular by hypotenuse. So perpendicular by hypotenuse means A by R, because sin theta, with theta this will be the perpendicular and this will be the hypotenuse, A by R. Here we consider the magnitude of this position vector. So sin theta equals to A by R. So cos phi equals, because sin theta equals to cos phi, so cos phi equals to also A by R, and A equals to R cos phi, so R equals to A by cos phi. So here we find out the value of DL and R. R equals to, we get A by cos phi. Now we find out L. So L means this distance is L. This OQ equals to L. So from this triangle, if we want to write or want to find out the expression of L, so we can write L equals to tan phi equals to L by A. Tan phi, this angle is phi. So phi respect, this will be the perpendicular, this will be the base. So L by A. So L equals to A tan phi. Now if we differentiate both sides, we get DL equals to A sec square phi d phi. Now we put this to value in this equation in place of DL and in place of R square. So after putting these values, and if we calculate this one, you get dB equals to mu 0 by 4 pi I cos phi d phi by A. And the direction, how we can direction? This is the current direction. So into the paper, normally into the paper, that's why I will mention over there, that is a cross sign. Now this is only for this small current element DL. Now if we find out for the whole wire, whole conducting wire, so that's why I will draw as a dotted line, and this from this end it will make the one angle phi 2, and from X it will make the angle phi 1. So we can say that it will move from phi 1 to phi 2, and as phi 1 is the opposite direction, that's why we consider phi 1 as a negative. So the magnetic field due to the whole conductor, B equals to integration of dB. So integration minus phi 1 to phi 2, we put the values, expression of dB that we already find out dB equals to. So if we put the limits, we get B equals to mu 0 by 4 pi I sin phi plus sin phi 1 plus sin phi 2 by A. This is the ultimate expression of the straight current carrying wire. Now here also be a small special cases also be there. If that wire, XY wire, if it will be a infinitely long, and the P point is lies near the middle of the conductor, conductor. So this phi 1 and phi 2 also be a 90 degree. middle of the conductor. So middle means here, so if the P point is lies near the middle point, so the phi 1 and phi 2 also be a 90 degree. So in place of phi 1 and phi 2, if you put the pi by 2, we get BM. BM means at middle. Okay. Mu 0 by 4 pi 2 I by a, that will be mu 0 I by 2 pi a. So you remember this expression. This is a very important expression, and the numericals also come like this way. So you just read it carefully, that if it will be written over there, that infinitely long wire, then you can use this formula. Now the conductor XY is infinitely long, but the P lies near the end X or Y. That means this P point lies either here or here. Any one end, either X or either Y. So what we can write, any one angle will be 0. So here I will consider the P point lies at the end Y. So phi 1 equals to 90 degree, that will be the perpendicular, and phi 2 equals to 0 degree. So if we put it over there in this equation, we get BE. E means that end, any end. BE mu 0 I by 4 pi a. So if you compare these two equation, we get BE equals to half of BM, because here mu 0 I by 2 pi a, if we multiply with a half, we get this expression. So the value of the magnetic field at any end due to an infinitely long wire, it will be the half of the if the point P lies at the middle, it will be the half of this BM. I hope it is clear. You understand this one? Okay. Next, another one application. This is magnetic field due to an circular current loop at the axial point, not at the center. I will discuss this one at later. This is a circular wire. This is its axial point. Axial point P. We find out the magnetic field. So this distance is x. This will make a 90 degree, and this is OC is a radius of the circular wire. This is A. So here the current in this anti-clockwise direction. So if we consider, so just first, if you just consider the first half. This is a circular wire, so this is the first half, upper half. Then we consider the lower half. So upper half we consider at the top a small current element DL. The distance from P, that will be R, and this is X. Okay. So if this will make a angle phi, so whatever the magnetic field will be created due to that small current element, that is perpendicular direction PQ dB. So the angle between the dB and d cos phi, that is the vertical component, that is also be a phi. And same if you consider the small current element at lower bottom, so you get the same. So this angle is phi, then this angle, this dB cos phi and dB also be a phi. So first of all, we at an R is the position vector of the P related to the element DL. So then from Vasavat Law, what we can write, mu 0 by 4 pi ideal sin theta by r square, due to from this one. Now this one is a very small, so this DL and this R makes angle 90 degree. So sin theta value is 90 degree. So here I will write this, everything is written over there, the language. So this language you can use for examination purpose, very small language, and this is a very important language statements. So DL perpendicular to R, so theta equals to 90 degree, sin 90 is value 1. So if we put it over there, sin 91, so we get dB equals to mu 0 by 4 pi I dl by r square, this equation. Okay. Now this dB lies in the plane of the paper perpendicular to the R, okay. dB is perpendicular to the R for both direction. Now so dV can be resolved in two components as per the vector addition law. So one is a vertical component and one is a horizontal component. So because this angle is phi, so this is a base. So base one, that vertical is a dB cos phi and this is a dB sin phi. Same here, if you consider the current element at bottom, so you get the dB in this direction. So this dB also resolve in two components. This is the dB cos phi because this angle is phi, so this angle also be a phi, and dB sin phi. So from here you see that for both the elements, current elements, dB cos phi is a opposite direction. dB cos phi are in a opposite direction. So these two are cancel each other. So whatever the magnetic field we get at point P, at axial point P, that will be due to the dB sin phi. So this dB sin phi for both component of dB will be added up. Okay, so we can write the total magnetic field B equals to, so everything is written over there. This dB resolve into components, dB cos phi, dB sin phi. Okay, dB resolve into components at the bottom of the same, and this opposite to the cos phi components are opposite to each other and cancel out each other. So sin phi components due to all current elements dl get added up along the same direction. So total magnetic field B equals to integration dB sin phi. That if we put the value over there, dB expression I will get from here. This will be, is it clear to everyone? This camera some problem. Yes, now it is okay. So dB, this is the equation of dB, expression of dB. So if you write it over there, sin phi means A by R, you put it over there, you solve this integration and you get B equals to mu 0 I A square by 2 into A square plus X square to the power 3 by 2. In place of R, you can also write R A square plus X square to the power half, because this is the R. So this is a triangle. So R equals to perpendicular square plus hypotenuse square to the power half. Pythagoras theorem. So this will be the expression B equals to this. Now here we consider one number of turns. If n turns are there, n number of turns in the coil, so just multiply with the n. Mu 0 n I A square by 2 into A square plus X square to the power 3 by 2. Now here also we have special cases at the center of the loop. That means R equals to 0. At the center of the loop here. So that means R equals to 0. No R is there. Sorry, not R equals to 0. That will be X. X equals to 0. Very sorry. That because if point lies here, so X equals to 0. No X is there. So if X equals to 0, so from this expression, what you can write? This X term is 0. So A square 2 cancel. So 2A cube. So you write mu 0 n I A square by 2A cube. So 1A cancels. So mu 0 n I by 2A at the center of the loop. And if we consider that X, the distance X is very greater than the radius of the circular loop. So we can neglect the A square term. So if we neglect the A square term, so only X square term is there. So 2 to cancel. So we get 2X cube. So mu 0 n I A square by 2X cube. This is the axial point lying far away from the coil. If the P point is lies very far from the coil, then we can use this one. Okay. Now the magnetic field at the center of the circular loop. So this is a circular coil. The current is flowing in a clockwise direction. At a point O, we discuss we derive the expression of dB due to this small current element. Okay, so due to this this is a very small current element. So this small current element, this distance A or the radius of the circular loop A will be 90 degree perpendicular to each other. And if we use the right hand thumb rule, so you see that this is the direction of current and the direction of the magnetic field is normally into the paper. That's why I will mention as a cross sign. This is very important for this chapter. You have to mention the direction of magnetic field with this sign, either cross sign or dot sign. So if we apply that Vasavat Law, dV equals to mu 0 by 4 pi I dl sin theta by A square and theta equals to 90 degrees. So sin 90 value is 1. So we get dB equals to mu 0 4 pi I dl by A square. So this is for only this small current element. So we can consider this whole circular loop is a summation is consist with this small current element dl. So if you consider dl here, so you get some same expression. If you consider dl here, you get the same expression. And you also get the same direction of the magnetic field in this direction. So you placed it here like this way. So this is the into the paper. So the total magnetic field, we just integrate both sides. B of integration this one. So mu 0 by 4 pi I. DL means the circumference of the circular wire, that is 2 pi a. So we get mu 0 I by 2a. If n number of turns are there, so mu 0 n I by 2a. This expression we get to mu 0 ni by 2a. Mu 0 I, here I will consider one number of turns, so n mu 0 ni by 2a. So we get the same expression here also. Okay. Another one derivations that is related to Ampere's circuitual law, that already I will discuss in that previous video. So I will upload with a language or with a statement later. So to now we discuss some numericals related to this derivations. What we discuss now, that way. So first, and this type of numericals is very important from this chapter. First one, a wire is placed along the north-south direction, carries a current of 8 ampere from south-north direction. So this is the south-north direction means this one. So this is 90 degrees. So south-north direction, this angle will be 45 degrees, and this distance is 200 centimeter. And due to the 1 centimeter, so DL is given, that is 1 centimeter piece of wire at a distance northeast direction. So I equals to 8a, DL equals to 1 centimeter converted to meter, R equals to 200 centimeter converted to meter, theta equals to 45 degree. I hope you understand why theta equals to 45 degree. So now we directly use the Vasavat law. So whenever you solve the problem, you have to write first the law, not with a value, the full law, that mu 0 by 4 pi I dl sin theta by r square. Because to write down this formula, you get the half marks. If you don't write, then your half marks will be deducted. Now you put the values over there. If you calculate this one, you get 1.41 10 to the power minus 9 Tesla. This is the magnitude. But here one more important thing, that is direction. So direction of the magnetic field at point P. So this is the current direction. So this is into the paper. That's why I will mention over there with a cross sign. And we also mentioned here that into the plane of the paper normally. Clear? This is very important. Don't forget to mention the direction. Next, this is very important. This type of numericals will come many times. A current element delta L equals to delta X I hat is placed at the origin and carries a large current I equals to 10 ampere. What is the magnetic field on the y-axis at a distance of 0.5 meter? Delta X equals to 1 centimeter. So this is a delta X, the small current element, delta L, delta X I hat means positive X direction. It carries a large amount of current, 10 ampere, so I equals to 10 ampere. So at a distance R, that distance is 0.5 meter. We can at a point P, we consider we find out the magnetic field, value of the magnetic field. Okay, so we use the Vasavat law. We write it over here and we put the values. Theta, here you see that this X and Y are always axes are perpendicular to each other, so theta equals to 90 degree. We get 4 into 10 to the power minus 8 Tesla. The direction, the current will flow in this direction. So if you put your right hand like this way, so your other four fingers outwards from the paper. So it is outward from the paper, that means dot. That's why I will mention here dot. Or you can use like this way, so that dB will be the direction of dl cross r. So dl cross r means, dl means delta x I hat cross y j hat. R means in y direction. So I cross j, that is k hat means positive z direction. So here you can see with this the direction magnetic into the paper or outward from the paper, and which direction, that means which axis, because two axes is there. So here you get I cross j means k hat means positive xz direction. So the magnetic field value is this one, magnitude is this one, and the direction is positive z direction. Next, this is also very important. a small current element ideal, dl's value is given, I is given. You can solve this one I will here write here the scalar form. You can also use the vector form. Try to in your home use the vector form I dl cross r I r vector by r cube. You can also easily get this directly. You get this value with the magnitude and the direction. Try to in your home with solve with a vector form. And here also the we find out dB this following points. So in this one I will solve by using the vector form. So try to in your home. Here I will use the vector form. Try to in your home to solve this problem with a vector form. Sorry, some important call is there. Okay, so how we can solve this one? Let's see. dl equals to 2k hat is given, I equals to 2a. So first r hat equals to 3i hat, x equals to 3 meter is given. So positive x direction, so that will be the distance. R hat equals to 3i hat. This is the vector form. So dl 2k hat, r hat 3i hat by r cube. So we get k cross I j k. I cross j means k hat, j cross k means I hat, k cross I means j hat. So k cross I, that will be j hat, and this is a positive y direction. J hat means positive. Okay, second one is given minus 6 I hat. Okay, so minus means 6 of minus I hat, opposite direction. If this is the positive x, this is the minus x, this side. That's why minus I hat. So the same way here I will put the magnitude only, because r is the magnitude. So only 6, not the minus 6. So you get k cross minus I, that means minus j. Minus j means negative y direction. This is a positive y, this is a negative y. And 3 number, dl equals to 2k hat, z equals to 3 meter, r equals to 3k hat. So r equals to 3k hat, k cross k, that will be 0. That means the same axis. In the z axis we find out the magnetic field. How it can be possible? Okay, so k cross k, that will be 0. So we get 0 for the third one. I hope you understand. So you also try it in your home with the vector form. Next and last numerical, 2 infinitely long. This is also come once in a board's questions, 3 marks questions. I don't remember it either. It will be 2017 or 18. Okay, 2 infinitely long insulated wires are kept perpendicular to each other. They carry currents. I1 equals to 2 ampere and I2 equals to 1.5 ampere as shown in this figure. So we find out at point P the magnitude and the direction of the magnetic field. So 2 wires. So due to the 2 wires we get the 2 magnetic field, and then we add it up. So we get the total magnetic field at point P. And second one, if any direction, any one, either I1 or I2, if we change or if we reverse, then what will be the effect of the magnitude of the magnetic field at point P. So first we find out this one, magnitude and direction. So because this is here mentioned, 2 infinitely long insulated wire. 2 infinitely long insulated wires. So which formula we used? This one, mu 0 I by 2 pi a for 2 infinitely long wire. So mu 0 I by 2 pi a. So for first wire, B1 equals to mu 0 I1 by 2 pi a1 due to this one. So a1 means 4 centimeter converted to meter. Mu 0 means 4 pi into 10 to the minus 7. This one I1 equals to 2a. So if we put it over there, we get 10 to the power minus 5 Tesla. Same for I2. Same for I2, if you find out, you get the same value, 10 to the power minus 5 Tesla. And direction, this is I1 into the paper. This is I2. This is I2 into the paper. Okay. That means like this way. Sorry. This like this way. This is I2 into the paper. This is I1 into the paper. That's why I will write as a cross side. Okay, so we get B1 and B2 for first wire and the second wire. So total magnetic field we added up. So 10 to the minus 5, 10 to the minus 5, 2 into 10 to the minus 5 Tesla, and direction normally into the plane of paper. Okay. Now the second question, if anyone will be reversed, suppose I2 is this side and I1 remains. So if I2 is this side, so the P point outward direction, the magnetic field outward direction. Now because here we get the same magnitude 10 to the minus 5, but in a opposite direction. The two fields are in opposite direction, so they will cancel each other. So the total magnetic field at point P will be 0. So if we reverse any current of any one of the wire, the two fields will be in opposite direction, so the B equals to 0. Okay, and then next, the Ampere's circuitual law, that solenoids with the statement and some numericals also be there. I will upload later. I hope this problems you understand. If you have any doubt, please inform me in a comment box. Have a nice day. Stay home, stay safe. Tata, bye bye.